Assalamu alaikum. This is Nabil Rajab Basha. I am a medical intern from Faisal University, and today I will explain the topic of acid-base balances. So I believe my colleague Ala Hamid stopped at this slide, somewhere around here. I will take over from this point. So let's start with the first objective, which is the production of acids and bases in our bodies. The main acid that is produced in our body continuously is CO2. As you can see, just bear with me for a moment. So as you can see, here we have glucose, and it is metabolized down glycolysis, down the TCA cycle, and so on. And as a byproduct of glucose metabolism, we have the production of CO2. So CO2 is a product of metabolism. And we produce around 20,000 millimoles of CO2 per day. And this is a huge amount, and we have to get rid of it. Fortunately, CO2 is a volatile acid, meaning that it can be easily excreted throughout the respiratory system. So here is CO2 is produced by continuous metabolism in peripheral tissues, and it travels through the blood to the lungs, and then it is expired. So CO2 is no hassle. It's not a big deal. We can easily get rid of it. And before moving to the next point, let me touch upon these reactions. So as you can see, carbohydrates and fats, they produce CO2 as they are metabolized. They produce CO2, which is easily excreted by the respiratory system. Amino acids, on the other hand, can be metabolized into hydrogen, which is, of course, an acid, or hydroxide, which is a base. So this depends on the amino acid itself, on the type of amino acids. Now, we don't need to memorize all of these, but all what you need to know is that sulfur-containing amino acids and cationic amino acids, they produce hydrogen ions, whereas anionic amino acids produce hydroxide. Now, if you add all hydrogen that is produced every day to all hydroxide that is produced every day, the net result is going to be 80 millimoles of hydrogen. So as you can see, here is the hydrogen that we produce every day, and here is the hydroxide that we produce every day. Each one is produced from specific amino acids, but the net result is the production of 80 millimoles of hydrogen, which is an acid. So we don't want our bodies to enter the state of acidosis, because if I have hydrogen, then pH is going down, and this will affect the hemostasis or the physiology of my body. This is why we have to deal with this hydrogen. Unfortunately, and unlike CO2, hydrogen is not a volatile acid. So it cannot move from peripheral tissues to the lungs immediately and get expired. Hydrogen has to be excreted mainly by the kidney. It's not a volatile acid. It's called a fixed acid. So here is the kidney. Here's, as we can see, the blood is in contact with the tubular cell, or to be specific, the alpha intercalated cell. And this cell is in turn facing the tubular lumen. Now, we said that we have 80 millimoles of hydrogen that we want to get rid of to prevent our bodies from entering acidosis. As you can see, this is hydrogen. So I want to excrete it. It will be excreted through pumps, and it will enter the tubular lumen, and it will be washed away with urine. Okay, so hydrogen is excreted from the kidney to the urine, and then we get rid of it. Now, the issue is hydrogen will enter the urine, and the pH of the urine will become acidotic immediately, and there will be no room to accept more hydrogen. There will be no, let's say, concentration gradient for hydrogen to move across the membrane from the intercalated cell to the urine. This is why we have buffers. And buffers in the urine are of two types, phosphates and ammonia. So as you can see here, we have hydrogen phosphate. It will bind to hydrogen and form dihydrogen phosphate. So this is how we buffered hydrogen, and we will prevent the sharp decrease in pH. Okay, we will prevent the sharp decrease in pH. Will prevent urine from becoming acidotic. The same thing applies to ammonia. Now, ammonia, we get it through the metabolism of glutamine. You don't have to know that, but we get ammonia, and ammonia NH3 enters the urine, and in the urine it accepts hydrogen, forming ammonium, which is NH4. So it buffered hydrogen. And when these hydrogen ions bind to ammonia and bind to phosphate, they will leave a space for more hydrogen to enter the urine. This is how we get rid of hydrogen in the kidney. Now going back to ammonia, just since it is depicted here in the picture, I'll quickly go over it. We have glutamine coming from the blood. The glutamine is broken down into ammonia and alpha ketoglutarate. And alpha ketoglutarate will find its way through the TCA cycle and will move in reverse to produce glucose. This is how the kidney takes part in gluconeogenesis. This is more biochemistry related. You don't need to know it for the sake of the renal exam, but I thought I could explain it since it is here in the picture. Because as we know, the main organ of gluconeogenesis is the liver, and the kidney accounts for around only 10% of gluconeogenesis in our body. So this is one of the methods by which the kidney produces glucose. So, okay, let's move to the next part. So we have blood buffers. Blood buffers are three types: the carbon dioxide bicarbonate system, hemoglobins, and plasma proteins. So let's start with the first one, bicarbonate. How is bicarbonate a buffer? Let's say in the lab setting, I have a solution of sodium bicarbonate, and I add to it hydrochloric acid. Now, as we know from the equation or the reaction of carbonic anhydrase will catalyze the formation of carbonic acid from hydrogen and bicarbonate. And of course, because we have chloride and sodium, we'll end up with sodium chloride. Now, carbonic acid is further broken down into CO2 and water. And in the human body, when we end up with CO2 and water, we can easily excrete them through the lungs or other mechanisms. So this is how bicarbonate in our body plays a role to maintain pH. If you add any acid to the blood, it will be buffered by bicarbonate. You will end up with the carbonic acid, which dissociates into CO2 and water, and they are easily excreted. This is how you maintain a normal pH in the human body. Another buffer is hemoglobin. So I showed you this picture before. We have CO2, as I told you, it leaves the peripheral tissues, moves in the blood, and then expired by the lungs. But the process is actually, it's not as simple as it sounds. So CO2 is produced by metabolism, and then it will react with water. It will react with water to form carbonic acid. If we go back to the equation, CO2 in the peripheral tissues, it reacts with water to form carbonic acid, and carbonic acid in turn will form hydrogen and bicarbonate. And these travel all the way through the blood until they reach the lungs, here, and then the equation will move the other way around again. Bicarbonate will join hydrogen, will join carbonic acid and form CO2 and water. Okay, so we're done with the second buffering mechanism. Let's move to the third buffer, which is plasma proteins. Plasma proteins, for example, albumin, are buffers. Let me give you an example. Here we have albumin. It's negatively charged. And albumin has to be bound to a positively charged atom or molecule. So here we can see albumin bound to hydrogen. So in case of acidosis, or let's say acidemia, in the presence of huge amounts of hydrogen, hydrogen is going to bind to albumin. This is how albumin prevents hydrogen from accumulating in the blood and prevents from decreasing. And it also works the other way. We want hydrogen to move to the blood. So albumin is going to donate hydrogen and it's going to bind less hydrogen. As you can see here, we have only one hydrogen in comparison to the state of acidemia, where we have 3 hydrogen. So albumin is a buffer and it controls our pH. And I'm giving you a scenario that is clinically relevant to this concept. So this concept is not only important for physiologists, it is also important for us as physicians, because in the state of acidosis, as I said, hydrogen is going to bind to albumin to buffer the excess amount of hydrogen. However, this will be at the expense of calcium. Calcium is going to be displaced from albumin. And this will result in increased ionized calcium. Okay? So you don't need to know the relation between calcium and hydrogen. I'm just giving an example of how important albumin as a buffer in acidosis, in alkalemia, and so on. But the one point that you have to bear in mind is that albumin and plasma proteins are buffers, and they prevent alterations in pH by binding and releasing hydrogen ions. So let's move to these parameters. Dr. Shams listed these for you. pH, as you know, it's from 7.35 to 7.45. The body can tolerate a low pH of 7.8 and a high pH of 8 only for a few hours. Few minutes. This would be a severe medical emergency. And we also have CO2, which usually indicates the respiratory function, and bicarbonate usually indicates the metabolic function. As Dr. Shans said, ignore the actual bicarbonate. We're concerned about the standard bicarbonate. The standard bicarbonate in the blood, which ranges from 22 to 28. So what are buffer bases? Buffer bases are simply all the bases in the blood, including bicarbonate and other bases. We can see bicarbonate and other anions that may accept hydrogen, or other bases in general. This is the total concentration of all bases. It's known as the buffer bases. Now, the base excess is a way to express, it's a concept to express how far we are from the normal amount of bases. In other words, how far we are from the normal level of bicarbonate. So let me give you an example. So, okay, let's go over this one first. I mentioned the normal ranges. Note that the base excess is usually from -3 to +3. So what do these numbers indicate? As I said, it indicates how far we are from the normal value of bases, or normal value of bicarbonate. Let me give you an example to make it easier for you. Now, this is a real venous blood gas drawn from a patient to assess his acid-base status. This is a patient with a condition known as diabetic ketoacidosis. And as you can see, his pH is low. This patient is in severe acidosis. He's 6.8. This is a medical emergency. And I don't know if you can see, but here is the bicarbonate. It's only 2.2. And under the bicarbonate is 30. So what does that mean? It means that we are 30 millimoles below the normal level of bicarbonate, or below the normal level of bases. You know, these are synonyms, bicarbonate and bases. So it means that the normal bicarbonate in this patient, it should be around 32. It's just an approximate number, but it means that we are 30 millimoles of bicarbonate below the normal value of bicarbonate. The base excess here is minus 30, so the normal bicarbonate should be the one that we have, the actual bicarbonate plus the base excess. To be honest, it's just another way of it's synonymous with bicarbonate. So we can use base excess or bicarbonate. Just it gives you an idea about the metabolic issue of the patient. Okay. And then let's move to, so I think you know that already. pH lower than normal is acidosis. pH higher than normal is alkalosis. So let's say we have a patient with acid-base abnormality. How to determine the acid-base abnormality? We look at the three main parameters: pH, bicarbonate, and CO2. pH, bicarbonate, and CO2. An easy way to remember it or to simplify is if pH and bicarbonate are going in the same direction, this is a metabolic issue. For example, let's say that the patient is having a low pH of less than 7.35. The pH and bicarbonate are in the same direction. They are both going down. We drew a venous blood gas, a VBG from the patient, and we read pH and bicarbonate and CO2 and so on. We see that his pH is low, and both pH and bicarbonate are going in the same direction. If they are both in the same direction, this is a metabolic issue. And then we look at the pH. It's as you can see, it's decreased. So this is acidosis. Of course, it's not alkalosis. So this is a metabolic acidosis. Usually in respiratory acidosis, the pH is also decreased. However, bicarbonate would not be low. Bicarbonate would be normal. Usually bicarbonate would be normal or high to compensate. Okay, but it would not, bicarbonate and pH would not go together in the same direction. So it would be normal or high. In arterial CO2, we can see here it's high. Why? Because I told you that this is a respiratory acidosis. So the CO2 here is an indicator of the respiratory status. Why is CO2 accumulating? Because we are not excreting enough CO2 in the first place. So this is a respiratory issue. And the pH is low and the CO2 is accumulating, so it's definitely a respiratory acidosis. Now, the same concept applies to alkalemia or alkalosis. pH is high, and we look at bicarbonate. Is it going in the same direction with pH? Then this is metabolic. And the pH is high, this is alkalosis. If they are not going in the same direction, it should be a respiratory problem. Of course, this is oversimplification, and in clinical practice, you don't do that. But for the sake of exam, you can do this. You can rely on this method. In respiratory alkalosis, what happens in respiratory alkalosis? Let's say that I am very anxious. I'm scared about the exam, so I'm hyperventilating. What happens is I will excrete huge amounts of CO2 because my respiratory rate is above normal. It's, let's say, 30 per minute. So I'm excreting huge amounts of CO2. My CO2 is going low. And as per the equation of Henderson-Hasselbalch, if CO2 goes down, the pH goes up. So this is how respiratory function may result in respiratory alkalosis. If we have hyperventilation, we're excreting huge amounts of CO2, we'll have respiratory alkalosis. And to be honest, this is not important, but you know, since Dr. Shams need you to know it, then you have to know it. For this is you know, usually physiologists are concerned with these details. We have respiratory acidosis, a patient with respiratory acidosis. Let's say someone with the CO is accumulating huge amounts of CO2. Now, as per the equation, if I increase CO2, pH is going to decrease, right? So for respiratory acidosis, there is an immediate compensatory mechanisms that occurs within, moments, not even seconds. CO2 will react with water to form bicarbonate and hydrogen. So we end up with we have increased bicarbonate, and if we go back to the equation, if we increase bicarbonate, this will somehow compensate for pH. It will prevent pH from going down, because if bicarbonate goes up, pH has to go up. So this is only partial compensation. This mechanism is not completely efficient, and it will be offset by the increase in CO2. CO2 is the kidney will come to play, and the kidney will try to maintain more bicarbonate. The kidney will try to increase bicarbonate more than the buffer mechanism that we already have. So bicarbonate will increase. Why? Because the kidney is reabsorbing bicarbonate in the proximal tubules. So we have a higher increase in bicarbonate, and then the pH can go back to the normal levels. This is how we compensate. This is how we compensate. So moving on to this part, as you can see, the base excess is 0. It's normal. As we said, the base excess is from -3 to +3, and this is expected because the base excess is an indicator of metabolic issue, respiratory acidosis. So the base excess is normal. And if you want to know the physiology of it, then let's go back to the equation. As we have an increase in CO2, it binds to water, it forms bicarbonate and hydrogen. Hydrogen in turn is going to bind to other anions, other bases that will accept, and bicarbonate is still here, and it will be increasing even more because the kidney takes part in the compensation. So we end up with high bicarbonate and low other anions. We have less number of other anions and higher number of bicarbonate. So the end result is the total number of bases, the total number of bicarbonate, and the other anions is the same. But I think this is very detailed, and you don't need to know it. What you need to know is that the base excess, which is an indicator of a metabolic disorder, is normal in respiratory issues. So this is what I was talking about. Here is the normal physiologic point. Let's say someone has respiratory acidosis, he cannot excrete CO2 because of a lung issue. So his CO2 is going to move. Here is CO2, it's 40. It's going to move to this line and the next line, and let's say it reached CO2 of 80. As you can see, the pH went down to 7.2. Why? Because when I increase CO2, the pH goes down. Okay, and then there will be a compensation by the kidney. As you can see, as Dr. Shams labeled for you, it's renal compensation. So the kidney will try to reabsorb bicarbonate and increase the amount of bicarbonate in the blood. So you can see that bicarbonate is moving up from 30 to 40. And we are shifting the pH a little bit back to normal levels. This is how we are maintaining or trying to maintain normal pH. Okay? I hope it's clear. Metabolic acidosis, same concept. Let's say that we have an acid that just entered our body. It will result in increased amount of hydrogen, and hydrogen will, if hydrogen increases, obviously pH will decrease. The body will enter the state of acidosis, and the immediate compensatory mechanism in metabolic acidosis is the lung. The lung will hyperventilate. So we have hydrogen and it's going to bind to bicarbonate, the formation of water and CO2, as you can see in the image, and CO2 will be expired by the lungs. So the lungs will try to prevent the pH from going down because it is excreting CO2. And this is the respiratory compensation. So again, when we increase acids in the blood, it's going to be buffered immediately by bicarbonate and then will be converted to water and CO2 and then excreted by the lungs. This is how the lungs will try to compensate and prevent severe acidosis in the body. Okay? And as you can see, if we increase hydrogen, we end up with less bicarbonate and less other bases because hydrogen will bind to both bicarbonate and other bases is going to be buffered. So they both decrease. They both decrease. So total the net result of bases, including bicarbonate and other bases or other anions, is going to decrease, and uh, the base buffer is going to be less than normal, or in other words, total amount of bases is less than normal. So the base excess is going to be in minus. It's going to be in minus. And this is how base excess gives you an idea about uh, uh, the metabolic state of our body. So base excess is only altered in metabolic acidosis or metabolic alkalosis. It's not affected in respiratory acidosis or respiratory alkalosis. Okay? Okay. And again, here we have metabolic acidosis. We can see that we're moving to the left, decreasing the pH. And why? Because bicarbonate is going down. Bicarbonate is going down. Bicarbonate is going down. So as we go down the bicarbonate, as we go down with bicarbonate, we're moving to the left, and we have decreasing levels of pH. We're entering the state of metabolic acidosis. So immediately within seconds, the lungs will respond and they will try to excrete CO2. So as you can see at this point, I'm at level 40 of CO2. The lungs will hyperventilate and I will move to level 20 of CO2. You can see if we follow this line, it's 20. And as we went this way, we moved the pH from 7.2 to 7 point, let's say 3, for example. So this is a compensatory mechanism, okay? And it is driven mainly by the lungs. This is what happens in metabolic acidosis. And this is the same concept, just uh, follow what I said, and you will end up with these points. If you try to pin all of these points, you'll end up with this image. And to be honest, this graph is not very important. Like no one does this in clinical practice. You don't have to do it. You just need to know what you need to know from this lecture is how to uh, tell uh, acidosis from alkalosis and how to describe the appropriate compensatory mechanisms. Okay, so I will skip these slides quickly. Okay. As I said, in if we have a low pH, a pH of 7.2, and a high arterial CO2, and a normal bicarbonate, or a normal base excess. If base excess is normal, it means that there is no metabolic issue. And we look at the CO2, we can see that it's much higher than normal. The highest level of CO2 is 45, but here it's 60. So it means that the body entered acidosis because of increased amounts of CO2. So this is mainly a respiratory issue. This is a respiratory acidosis. And as I said, uh, uh, here bicarbonate would be normal. It's not decreasing in the same direction. Okay. Let's move to the next slides. You can read this in your free time. So let's say that we have a metabolic acidosis. Let's say that we have a metabolic acidosis. Metabolic acidosis is usually of two subtypes, which is high anion gap metabolic acidosis and normal anion gap metabolic acidosis. What is high anion gap metabolic acidosis? It means that sodium is much higher than chloride plus bicarbonate. This is a high anion gap metabolic acidosis, and it has specific sodium is the difference between sodium and chloride plus bicarbonate is not high. This is a normal anion gap metabolic acidosis. Just give me a second. So let me use this image to explain to you. Now this is a normal physiologic state, no acidosis, nothing, everything is all right. And at this level we have an anion gap. Sodium, to understand. And this is a normal anion gap metabolic acidosis. So it's a type of metabolic acidosis. What happens in this metabolic acidosis? As in every metabolic acidosis, bicarbonate is going to decrease. Bicarbonate is going to decrease. You can see that here is the normal bar of bicarbonate. You can see how it shrinks to this level. And to maintain the negative charge in the body, to maintain electron neutrality, chloride in turn will increase to compensate for the decrease in the negative charge. So we maintain electron neutrality. Now, if you apply this to the equation, now sodium here is the same as sodium here. Bicarbonate went down from here to the last bar, bicarbonate went down. However, increased, chloride increased. Because metabolic acidosis with a normal anion gap has its specific causes, which are listed in this slide. Normal anion gap metabolic acidosis, as I said, high chloride replaces less bicarbonate. This is seen usually in diarrhea, in kidney disease known as renal tubular acidosis, in hydrochloric acid, and in carbonic anhydrase inhibitors, which are a group of drugs. Okay, now let's go back to explain the high anion gap metabolic acidosis. So what happens in high anion gap metabolic acidosis, just like in every other acidosis, bicarbonate is decreased. Bicarbonate is decreased. Okay. Here is the normal bar of bicarbonate and so who's maintaining the negative charge? Who's correcting the electron neutrality? It's actually the acid that came in the first place and caused this disturbance. These are a group of unmeasured acids, or this a group of unmeasured acids that came and caused this disturbance, and they cannot be measured in the lab. So when I subtract chloride and bicarbonate from sodium, the gap is going to be higher than normal. Why? Because I have less bicarbonate, I have less bicarbonate here, and in response there is no increase in chloride. So the sum of these two is way less than sodium. So this is the high anion gap metabolic acidosis, and it has its own specific reasons, like lactic acidosis, ketoacidosis, chronic renal failure, methanol, ethylene glycol, which is alcohol, rhabdomyolysis, which is the breakdown of muscles. So let me explain again. For example, if I have a lactic acid. In lactic acidosis, I have lactic acid. Lactic acid will cause, it's an acid, so it will take over here, and it will cause bicarbonate to decrease in number. And at the same time, chloride is not going to increase because lactic acid itself is maintaining the electron neutrality. So the end result is a huge gap because I decreased bicarbonate. However, I did not increase chloride. So there is a huge gap. So this is just a method to differentiate between the causes of metabolic acidosis. And the high anion gap metabolic acidosis are grouped under one word, which is mud piles. Let me type it for you here. Mud piles. Mud piles. M is methanol, U is uremia, which is seen in chronic kidney disease. D is diabetic ketoacidosis. P is propylene glycol. I is isoniazid and iron tablets. L is lactic acidosis. E is ethylene glycol. And C is salicylates, which is aspirin, salicylic acid or aspirin. And finally, we have two slides. These are just equations. To be honest, there is no point in clinical practice. Don't apply this. You never write down these equations and measure how much of sodium bicarbonate you need to give to correct metabolic acidosis. Actually, in clinical practice, even when someone is in acidosis, you rarely give them sodium bicarbonate. Why? Because sodium bicarbonate is a drug with many side effects, and it increases the risk of cerebral edema, which may lead to death. So we only use sodium bicarbonate in rare situations. We never do these equations in practice. This is at the lab level. Okay. But you can go over these equations. I don't think they are important. Sodium bicarbonate in clinical practice, we only use it when sodium when pH goes down to 6.8 or 6.9, which are very critical levels. And at these levels, there is a fixed dose of sodium bicarbonate that we give. There is a fixed dose of sodium bicarbonate that we give, and it's not related to these equations. We don't use these equations to determine the dose of sodium bicarbonate that we have to give. So to be honest, there is nothing to explain here. It's just these equations that Dr. Shams would like you to know. And I think that's it for today. If you have any questions, you can contact me. You can ask for my number from Ghazi. And I know that this topic is very complicated, but with time, as you do question banks, it's going to get easier for you. Nephrology is a very interesting topic, but at first glance, it seems very complicated. If you have any questions, let me know. Thank you so much for listening.